Today, we want to start looking at eigenstuff. This is a process that we're going to apply to square matrices. So let's start off with a square matrix. Let A be an n by n matrix. An eigenvector V of A corresponding to eigenvalue lambda. So eigenvectors have to correspond to eigenvalues. An eigenvector corresponding to eigenvalue lambda is a non-zero vector such that A times V is equal to lambda times V. The non-zero vector part is important because A times 0 will be any lambda times 0, because A times 0 will always equal 0. So the non-zero part is what we're interested in. What vectors just stretch or squish under multiplication by the matrix A? So let's look at this in the traditional way. We're going to start with a 2 by 2 matrix. Then we're going to start by finding the eigenvalues of A, and then use the eigenvalues to find a basis for each eigenspace. That is, find an eigenvalue for each, an eigenvector for each of those eigenvalues. Let's start with what we know. Let's suppose if V is an eigenvector of A corresponding to eigenvalue lambda, then A times V is equal to lambda times V. So it starts with AV is equal to lambda times V. Once again, this is going to be the traditional way. So all of you anti-determinant folks, I am also an anti-determinant folk, but this is the traditional way we get into eigenstuff. So since AV is equal to lambda times V, that means if I subtract these two, we'll get 0. If these two things are equal, then their difference will be 0. So this means that AV minus lambda V is equal to the 0 vector. We like 0 on the other side because that says homogeneous equation, and we know stuff about homogeneous equations. So what I want is to make a homogeneous matrix equation. Now I have AV minus lambda V. I can't just factor out a V because A and lambda, I can't subtract those. A is some square matrix and lambda is just a scalar. So here's what we do. We cheat a little bit. I'm going to insert an identity matrix into lambda times V. So I'm going to say A times V minus lambda times the identity matrix times V is equal to 0. The reason that I want to do this is that I want to be able to factor out the V to make a homogeneous matrix equation, but I can't subtract A minus lambda because lambda is a scalar and not a 2 by 2 matrix. So I'm going to insert an identity matrix. This doesn't change the value of lambda times V. So since we're dealing with a 2 by 2 matrix, lambda I is just a matrix lambda on the main diagonal and 0 off the main diagonal. There's the matrix lambda I. So now that I've inserted that identity matrix, I can factor out the V, and I can say A minus lambda times I times V is equal to the 0 vector. So here is a homogeneous matrix equation. So we have this homogeneous matrix equation where the matrix is A minus lambda I times V is equal to 0. Now here's what else we know. If V is going to be an eigenvector of the matrix A, that means V is non-zero. If V is an eigenvector, then V is a non-zero vector. So if V is an eigenvector, the equation A minus lambda I times V equals 0 is a homogeneous equation with a non-trivial solution. So V is a non-trivial solution to the homogeneous matrix equation. That means that the columns of A minus lambda I are not linearly independent. Or the columns of A minus lambda I are linearly dependent. Oops. So that means that the columns of this A minus lambda I are linearly dependent. So that means a lot of things. That means the matrix A minus lambda I does not have a pivot in every column. Since A minus lambda I is square, that means the A minus lambda I does not have a pivot in every row. That means one of the columns of A minus lambda I is a linear combination of the others. Since A is a 2 by 2 matrix, that means one of the columns that the columns of A minus lambda I are multiples of each other. And the other condition, conclusion that we can draw is that the matrix A minus lambda I is not invertible. And this is the traditional route, i.e. A minus lambda I being square is not invertible. And from here, we get that the determinant of A minus lambda I is equal to 0. Notice that this 0 is the scalar 0, not the vector 0. So we're looking for lambdas that make A minus lambda I not invertible. Let's look at the vector, let's look at the matrix A minus lambda I. So I have the matrix 7, -4, 2, 1. I'm going to look at the matrix A minus lambda I. So that's going to be this matrix, 7 minus lambda, -4, 2, and then 1 minus lambda. Once again, if V is to be an eigenvector corresponding to eigenvalue lambda, then V has to be non-zero. So that means V is a non-trivial solution to this matrix equation. And so that means the matrix itself is not invertible. So that means we want the determinant of this matrix to equal 0. So I want the determinant of the matrix 7 minus lambda, -4, 2, 1 minus lambda to equal 0. So since it's a 2 by 2 matrix, calculating this determinant is not really a big deal. We just do AD minus BC. So I do AD. Okay, this is too light. I gotta switch to a darker color. So 7 minus lambda times 1 minus lambda minus 2 times -4 is equal to 0. I just got to find the lambdas that make this equation true. This equation is the characteristic equation for the matrix A. So we call this the characteristic equation of A. So we just need to set this equal, we got this polynomial, we've set it equal to 0, we just need to solve this polynomial equation. So we multiply this out, we get 7, we're gonna get 7 plus 8 is 15. And then we'll have lambda is minus 7 lambda, minus lambda is minus 8 lambda. It's going to be 7 plus, so plus 15. And then we'll have a lambda squared. Now we just need to find the two lambdas that make this work. So lambda squared minus 8 lambda plus 15 equals 0. We can go the traditional route and factor this, because if we want to be old school, so we'll have a 3 and a 5. So lambda equals 3 and lambda equals 5. Those are our two eigenvalues. We got two eigenvalues of A. Of course, if we wanted to solve this characteristic equation with a little bit of style, we could complete the square, because it's going to be a lambda squared minus 8 lambda plus 16. We wouldn't write this part down, and then that would mean a minus 1. So lambda minus 4 squared minus 1. So everything within 1 unit of 4, that's 3 and 5. But the traditional way would be to factor this polynomial. But then you get crazy things happening, like lambda squared minus 8 lambda plus 16, or better yet, plus 17. And people will be like, oh, well, that's not factorable. But it totally is factorable, just not factorable over the integers. Maybe it's just factorable over complex numbers. What do you mean by factorable? But that's neither here nor there. That's just an algebra thing. So we have found the two eigenvalues of A. Each eigenvalue should correspond to an eigenvector. And we know those eigenvectors are going to be the non-trivial solutions to some homogeneous equation. So now for each eigenvector, for each eigenvalue, we need to find an eigenvector. For each eigenvalue, we find a corresponding eigenvector. So our matrix A was 7, -4, 2, 1, and our eigenvalues were 3 and 5. So for lambda equals 3, A minus lambda I is going to be, we'll have 7 minus 3 and -4, and then 2, and then 1 minus 3. So that's going to be the matrix 7 minus 3 is 4, negative 4, and then 2, negative 2. So what we want to do is write the non-trivial solutions to a minus 3i equals 0. So now what we need to do is solve. And for that, we're going to use an augmented matrix. It's a homogeneous equation. We don't really need an augmented matrix, but we're going to emphasize what we're doing. We've got 4, negative 4, 2, negative 2, 0, 0. And we're going to write the reduced or echelon form. So I'm just going to divide through by 4. So I'll have a 1, a 1/2, and a 0. And I can subtract the second row from the first row, and I'll have just zeros. So my solution set looks like x1 is equal to negative 1/2 of x2, and x2 is my free variable. So one such vector v, if x1 is negative 1/2 and x2 is 1. Here is one of the eigenvectors corresponding to eigenvalue 3. We can verify that this is correct by multiplying this vector by the matrix A. So let's grab our green pen for checking things. And I'm going to multiply A times negative 1/2, 1. So let's check. 7, negative 4, 2, 1 times negative 1/2, 1. So that's negative 1/2 the first column. Oops. Plus 1 times the second column. So negative 7/2, so negative 3.5 plus 2 is negative 1.5. And then 2 and 1 is 3. And this is just 3 times what we started with. Checks out. Notice that if I multiply v by some scalar, then I will also have another eigenvector. So we can think of v as a basis for an eigenspace of this matrix corresponding to lambda equals 3. So if I use any multiple of v, that is also an eigenvector. So any multiple scalar multiple, any multiple of v equals negative 1/2, 1 is also an eigenvector of A corresponding to lambda equals 3. So if, for example, you're not a fan of the negative 1/2, 1, you could also just multiply. So for example, if I just multiply everything by 2, I could have negative 1, 2 is also an eigenvector. So if I take 7, negative 4, 2, 1, and multiply it by negative 1, 2, because maybe you're part of the anti-fraction faction, You're just against the use of fractions. We're also going to get 3 times what we started with. So we got -7 plus 4 is -3. 4 plus 2. 4 plus 2 is 6. And so this is still 3 times what we started with, -1, 2. Still checks out. So in that way, we can think of -1/2, 1 as a basis for the eigenspace of the matrix A corresponding to eigenvalue lambda equals 3. So we can combine all this and we can say that the set containing this vector is a basis for the eigenspace of A corresponding to eigenvalue lambda equals 3. Notice that you can't just say basis for the eigenspace. It's the basis for the eigenspace corresponding to lambda equals 3. You can leave off the lambda part. But basis for the eigenspace is not enough. Basis for the eigenspace corresponding to 3. So that's 1 of the eigenvalues. Now we just have to do the same thing for 5, the other eigenvalue. So for lambda equals 5, a minus 5i will be 7 minus 5, -4, 2, and 1 minus 5. 7 minus 5 is 2. 1 minus 5 is -4. And so here we have, once again, a non-invertible matrix. So our homogeneous equation will have non-zero solutions. We need to solve a minus 5i times v is equal to 0. And we're going to use an augmented matrix like we do, 2, -4, 2, -4, 0, 0. And we can see how this is going to go right away. We're going to have 1, 1, 0 across the top. And we'll be able to cancel out the second row. We knew that that was going to happen because we knew we could not have a pivot in every column because these vectors had to be linearly dependent. Otherwise, we wouldn't have a non-trivial solution to the homogeneous equation. So in this case, we'd say V1 is equal to -V2, and V2 is free. So we go -1, 1 is an eigenvector of A corresponding to lambda equals 5. We can check if we multiply A by the vector -1, 1, we should just get -5, 5. So let's check. 7, -4 times 2, 1. Or sorry, 7, -4, 2, 1 times -1, 1. It's going to be -1 times 7, -4 plus 1 times 2, 1. And that gives us -5, 5, which is 5 times what we started with. So that checks. Similarly, any multiple of -1, 1 will also be an eigenvector of A corresponding to lambda equals 5. So we could say that -1, 1 is an is a basis for the eigenspace of A corresponding to lambda equals 5 in the same way that we wrote it up here. Notice that when I'm talking about a basis, I'm talking about a set of vectors. That's why the extra set notation shows up around the vector. There's only one, so if you left that off, that would be fine. Any questions? Right, this is how we can find eigenvalues and then use those eigenvalues to find eigenvectors. Let's pause the video here and talk about what we'll do with this.